welcome to the 40th lecture of this course. So, today we are going to discuss more on NP-Completeness. So, last time we defined the problem SAT and the problem 3-SAT, and I mentioned that historically SAT was the first problem that was proven to be NP-complete due to Cook and Levin. So, this was in the 1970s. And thereafter there was a sequence of problems which were shown to be NP-complete by the use of reductions. So, 3-SAT was one of the problems. So, it was shown immediately after that SAT reduces to 3-SAT. So, basically you can take a Boolean formula, an arbitrary Boolean formula, and convert it to a 3CNF Boolean formula, or a Boolean formula where every clause has exactly 3 literals, such that if the first formula is satisfiable, the second is satisfiable, and if the first is not satisfiable, then the second is not satisfiable. Okay. So, this you can try as an exercise, this is not very difficult to show. So, this all this argument gives an NP hardness proof of these problems. Okay. But what about containment in NP? Okay. So, how do we show, for example, that SAT is in NP? Okay. So, SAT certainly belongs in NP, and if we want to give the certificate based definition, so the certificate is going to be a truth assignment tau. Okay. Now, you just have to, so check if, so the Boolean formula is phi. So, check if phi comma tau is equal to 1. If so, then accept, else reject. Okay. So, observe that if we are given a Boolean formula phi and we are given a satisfiable a truth assignment tau, we can very easily plug in the values of the assignment onto the Boolean formula and check whether it evaluates to 1 or 0. So, that can be checked in polynomial time, okay, that is easy to check. But given just a Boolean formula, to check whether it is satisfiable, we do not know whether that can be checked efficiently in polynomial time, okay. Whether we can answer given just a Boolean formula whether it is satisfiable or not. So, one approach is to try all possible truth assignments. Okay. So, if the formula has n variables, there will be 2 to the power n many satisfying assignment, but that is not in polynomial time, that is exponential time. Okay. So, that is not an efficient algorithm. So, but this gives an efficient NP algorithm at least. So, this approach. Okay. So, what we are going to show next is how to use the technique of reduction to show that other problems, other NP hard problems and subsequently NP complete problems. Okay. So, recall this problem click. Okay. So, we had seen this problem a couple of lectures back. So, click is the problem of consisting of instances of the form g comma k such that g has a complete graph of size at least k. Okay, and we had shown that this problem belongs to NP. So, today what we will prove is that 3-SAT reduces to click, okay. And because we know that SAT is NP hard, this proves that 3-SAT is NP hard, and because 3-SAT is NP hard, this would prove that click is NP hard. So, we will look at this complete reduction. Okay. So, how does the reduction proceed? So, suppose as input we are given a Boolean formula. So, let me do it here. So, suppose we are given a Boolean formula phi, which is equal to, so it is a 3-sat formula. So, the formula consists of clauses, it is an AND of clauses, each clause has 3 literals. So, phi is equal to, let us say, L11 or L12 or L13. So, these are all literals, I am just naming the literals with L, and L21 or L22 or L23 and so on. We have LM1 or LM2 or LM3. Okay. So, the formula has M clauses, each clause has 3 literals, and of course, some of these literals can be the same. Okay. For example, I can have a variable x1 here and maybe again x1 here, or maybe I have for L13 I have x3 complement, and again in LM1 I have maybe x3. So, they can be any collection of variables. So, given a formula like this, I have to construct an instance of click. So, what is an instance of click? An instance of click is a graph and a number k. Okay. So, how do I construct the graph? So, I define, so construct G equal to V comma E as follows. Okay. So, V is defined as, so for every literal I will have a vertex. So, I have a vertex Vij such that Lij is a literal. Okay. Or I mean I can write this as I goes from 1 up to m and j goes from 1 to 3. Okay. And I define edges as follows. So, I will have undirected edges. So, let us say I have an edge between a vertex V I j and a vertex V I prime j prime. So, I have an edge between these two vertices if I is not equal to I prime. Okay. So, that is these two vertices correspond to literals that come from different clauses, and the corresponding L. So, L I j is not equal to L I prime j prime complement. Okay. So, first of all, they must come from different clauses, and one literal must not be the complement of the other literal. For example, if Lij is x1 and Li prime j prime is x1 complement, then I will not have an edge. Okay. I can of course have an edge between x1 and x1, I can have an edge between x1 and x2 complement, but not between x1 and x1 complement. Okay. So, to motivate and then I just output. Okay. So, that is my input. So, I will just output this graph G. Okay. So, actually I need to output more. So, I need to output a graph and also a number k. Okay. So, I need to specify that also. So, I will set k to be equal to this number m, that is the number of clauses. Okay. And then I output G comma k. Okay. So, this is the entire construction, and observe that this construction is clearly in polynomial time, because given a graph, given a Boolean formula, construction of this graph is very easy. Okay, because I just have to scan through all the literals, every pair of literal, and depending whether it satisfies these two conditions or not, I will just keep on adding edges. That is all. So, now why is this correct? Okay. So, before I talk about the correctness of this approach, let us look at a small example. So, I have a example here. So, suppose we have phi which is equal to x1 or x2 bar or x3, and then we have x1 bar or x3 or x4 bar and x2 or x3 bar or x4. What would be the corresponding graph? So, first I have vertices for all these vertices. So, this is for x1, x2 and x3. Okay. So, let us say this is my clause C1, this is my clause C2 and this is my clause C3. So, this corresponds to C1. Then I have 3 vertices which correspond to C2 and then I have 3 vertices which correspond to C3. Okay. So, this is let us say corresponding to x1 here, x2 bar, x3, x1 bar, x3, x4 bar, and I have x2, x3 bar and x4. Okay. Now, how do I add edges? Of course, x1 I will add, I will not have an edge from x1 to x1 bar, but to every other vertices I will have an edge. So, I have an edge from here to here, here to here, and from x1 to x4. From x2 bar I will have an edge to x1 bar, x3, x4 bar. I will not have an edge to x2, I will have to x3 bar and x4. Okay. Similarly, from x3 I will have to x1 bar, I will have an edge to x3 and x4 bar. I have an edge to x2, not to x3 bar and to x4. From this x1 bar I have an edge to x2, x3 bar and x4, and from x3 I have an edge to x2 and x4, and from x4 bar I will have an edge to x2 and x3 bar only. Okay. So, this is the construction of the graph corresponding to the Boolean formula phi. Okay. So, now why is this construction correct? Okay. So, suppose phi is phiable. Okay. So, what happens if phi is satisfiable? Let us look at this graph. So, if phi is satisfiable, by our construction, okay, there exists one literal for every clause that gets a value 1. So, there is a truth assignment, okay, there is some truth assignment which gives a value 1 to at least one literal in every clause. Okay. So, then there exists a truth assignment that gives a value 1 to at least one literal per clause. Okay. So, the claim is that if I pick this one literal from every clause, so this set of 1 literals from every clause gives a complete graph. Okay. Because observe that if I have two, let us say I have a literal L11 here and I have a literal L22 here, which gets a value 1, then clearly it cannot be that this variable is a not of this variable, okay, because then both cannot get the value 1. So, if both gets the value 1, it should not be the case that one is a negation of the other, which means that there is an edge between L11 and L22. Okay. And how many clauses do we have? So, since the number of clauses is equal to m, therefore, we have a complete graph of size m. Okay. So, I take this set of m literals, one per clause, and if I look at these the vertices corresponding to these literals in my graph, they will constitute a complete graph. Okay. Hence, I have a complete graph of size m. Okay. So, if phi is satisfiable, I get a complete graph of size m. Now, the other direction. So, let us look at the graph now. If G has a clique of size greater than or equal to, let me call it m, m and k are the same basically, because that is how I define this. So, if my graph has a clique of size greater than m, okay, first of all observe that it cannot have a clique of size strictly greater than m, for example, m plus 1, okay, because if you look at the vertices corresponding to only one clause, there is no edge between them, okay, and the number of clauses is equal to m. So, the maximum size of a clique can only be m. If I have m plus 1 vertices, then there are at least 2 vertices from the same clause by pigeonhole principle, which cannot be possible. Okay. So, if G has a clique of size greater than m, then it implies that G has a clique of size equal to m. Now, consider the clique. Okay. So, consider this clique. Okay. So, consider the literals corresponding to this clique. So, each literal must come from a different clause, first of all, that is by definition, and it also must be the case that because this is a clique, no literal is a negation of another literal in this set. Okay. So, set values to the variables such that each such literal gets a value 1. Okay. For example, if I have a literal x1, then I will just set x1 equal to 1. If I have a value, let us say x2 bar, then I will set x2 to be equal to 0, which would mean that x2 bar is equal to 1. So, that is what I mean that set values to variables such that each literal gets a value 1. And this assignment, okay, this assignment or truth assignment is a satisfying assignment for phi, which implies that phi is satisfiable. Okay. So, if I start with a graph which has a clique of size at least m, then I am able to show that phi is satisfiable. Okay. So, this shows both directions. So, therefore, we have proven that if we take the problem 3 sat, then we can reduce 3 sat to click, which shows that click is NP hard. Okay. Let us look at another example. So, this is a simpler reduction. So, this is called the independent set problem. Okay. So, the independent set problem is defined as follows. So, it is defined as set of pairs of the form G comma K, okay, such that G is a graph, G has an independent set of size at least k. Okay. So, what is an independent set? So, independent set is basically just the opposite of click. Okay. So, if you have a independent set inside a graph, it just means that there are no edges between any pair of vertices in that set. Okay. So, S is an independent set if for every pair of vertices u v in S, no edge exists. Okay. So, that is the definition. Okay. For example, if I look at in this graph example, if I look at x1, x2 bar and x3, so if I look at these 3 vertices, they form an independent set of size 3 because there are no edges between these 3 vertices. Okay. Similarly, if I look at these 3 vertices, they also form an independent set, okay, and so on. So, what we will show is that click reduces to independent set. Okay. So, we take an instance of click, let us say G comma K, and we give a function that outputs an instance of independent set. I need to give a different name. So, I will call it G prime comma K prime. Okay. So, this is very simple, this reduction. So, what essentially the reduction does is it computes the complement graph. Okay. So, G prime is the complement graph of G. So, wherever G has an edge, in G prime you will not have an edge, and if G does not have an edge, then in G prime you have an edge. Okay. So, let us say that I define G prime as follows. So, the edge set of G prime is defined as follows. Let me do it here. So, first of all, the vertex set of G prime is equal to the vertex set of G. So, they have the same set of vertices. Now, the edge set of G prime is defined as follows. So, u comma v is an edge in G prime if u v is not an edge in E of G. Okay. And this is equality, which means that this exactly consists of those pairs. Okay. So, every pair which is not an edge in E of G is an edge in E of G prime, and every pair which is an edge in G will not be an edge in G prime. Okay. So, that is the definition, and set K prime to be just equal to K. Okay. Now, the proof of correctness is, so this first of all the construction is simple, the construction is clearly in polynomial time, and the proof of correctness also is not very difficult to argue, because look at, first of all, look at an independent set of size k in G. So, if G has an independent set of size k, by definition the same set, if G has a complete graph of size k, by definition the same set will be an independent set in G prime, because there will be no edges between any pair of vertices in that set. And if I take an independent set here, by definition the same set will be a clique here. Okay. So, that is, it follows very simply. and one can also show that independent set is in NP, because again I will guess a certificate which will be a set of vertices, and I just need to verify whether for every pair of vertices in this set no edge exists. Okay. So, therefore, this shows that independent set is NP hard and subsequently NP complete. Okay. So, I will end my discussion here. So, let me give a brief review of what we have seen in this course. So, in this course we saw models of computation. So, our goal was to understand computation via different models, like what is the power of different computational models, what are the kind of problems that they can solve, what are the limitations of these computational models in the sense that what are the things that they cannot solve, and by understanding limitations we constructed models which had more power, which somehow were able to tackle these limitations. For example, initially we looked at finite automata, and we saw that there are languages which are not computable by finite automata. So, we defined context free grammars and push down automata. Okay, so, they were able to recognize some non regular languages, but then there were again languages which were beyond which were not decidable by a push down automata or a context free grammar. So, then we moved on to Turing machines, and we talked about decidable and undecidable problems. Okay. And in the region of decidable problems, we have this gradation of problems that are defined based on the amount of time that that it takes to solve a problem, and amount of space also. So, we look at various resources, and based on the amount of resources that a class of language uses, we classify these languages, and then we try to study properties between these languages. Okay. So, this is basically what we have seen in this course, and so that is all. Okay. Thank you.